Okay, so good morning, everyone. Thank you for joining this session. And I'm Jane Liu from Lamar University. And today I'm going to present our paper, Effects of Nonlinear Functions, Knowledge Graph Convolutional Networks for Recommender Systems with Yelp Knowledge Graph. So this is a work done by my student, Xing and me. And next, I'm going to start with our outline. A second. Okay, here. So first, we're going to just briefly introduce the topic, and then we're going to talk about the related work. Our work is focusing on recommendation systems. We're going to talk about the traditional recommendation systems, and then the knowledge graph-based recommendation systems that we focus on. And next we're going to talk about our proposed work, the knowledge graph processor, and we also analyze the various nonlinear functions for aggregators for using in the knowledge graph-based recommendation system. And then we're going to present our evaluation results and conclude and talk about future work. So as we know that the number of internet users and also the data generated every day just dramatically growing. So then, for example, in 2019, right, the number of internet users reached about 7.7 billion. And then the data generated, right, every day is about 2.5 quintillion bytes. And so things become more and more challenging, right, for users and also for the all these providers service, right, to cope with this dramatic data explosion. For example, lots of us watch Netflix, right? There's also other online streaming providers, and they provide more than 10,000 movies, right, and then TV shows for users to choose, right? So we browse and see which one we like, and somehow we also receive the recommendations. And then when we shop online, right, there's all these e-commerce websites. Like Amazon is the largest e-commerce website, right? They have built basically about 12 million products. So then from user side, right, so how do we find out something we like, right? We choose to watch which one to buy. And then from the provider side, right, how do we provide better user experience? And that's basically is a big challenge, right? It's getting more and more challenging. So then what are the solutions, right? There's all these different ways, right? There's a lot of research done on data analytics and on recommendation system. So if we just, if we're looking for something, right, we just search on that. And sometimes, right, we might not be able to find out what we're really interested in, right? So if from the provider side, if they can provide more personalized recommendation, right, that'll be very useful for better user experience. So recommendation system play an important role in all these applications, right? Search engines, e-commerce, right? Social media sites, and then all these online streaming services. And then there are different types of recommender systems. There are traditional recommendation algorithms. Okay, let me see here. They only consider the, like if you look at this example here, right? We have this is like a movie review, and then we try to recommend movies to a user. So if you look at these users, right, on the right side, they like different types of movies. So we have the movie M1, movie M2, and then the user David, like movie M2, right, and so on. So in the traditional recommendation systems, right, most of these are consider only the user and then the item relationship, right? So then this user likes this movie, right? This user likes this movie, and then it's based on the user and item relationship, right? And then the one we're focusing on here is the knowledge graph. It will take more information into consideration. So if we look at the left side here, for all of these movies, right, we will have actor information, right? Then the director information, producer information, and then all these other informations. So if we look at this for M1, right, we see actor A1, A2, and then the director, right? And similarly for other movies. Now, the difference between the knowledge graph-based recommendation system, it will take more information into consideration to build this knowledge graph to support better recommendation. So if you look at traditional recommendation systems, right, for all these recommendation systems, we'll try to solve either prediction version of problem, try to make a prediction, right? Predict the rating values for user item combination, right? Or ranking version problems, determine the top K item for a particular user, right? And one of these main approaches is a collaborative filtering methods, and that they're user-based and also item-based approaches. So if you look at this example here, right, we have for user A, B, C, and then we have the different types of fruit. So it could be a grocery store, right? And then there's apple, banana, pear, and grape. So based on this information, we have user, we have items, right? Then we look at the user A, right? We see user A. User A likes apple, right? And then banana, and then the pears, right? Okay. Then when we look at user C, right? User C. So user C also likes apple, right? And also likes pear. So this is the user and the item relationship. And then for user base, right? It will based on the user preference. When this type of approach look at, right, the relationship between the user and item, they will see that both A and C like apple, right? And also pear. So then they will recommend what A likes, which is banana, to C. So that's kind of user-based, right, recommendation based on the user preference, and they recommend some of these user likes to another user, right? But then think about another case that these are pretty like fruit we see every day, right? What about there are some fruit that we don't have it, right, in this record here? So what if we have a cherry, right, or some like other kind of fruit, right? How do we base on the user and item information to recommend this? And then think about if we have a new movie, right, that available on Netflix, right? And then there's no user ever watched that. I mean, could be right, some user watched it before. But then any new products on Amazon or any other e-commerce website, right? So then we are depending on this user, right, and the item relationship, the user based, right? So then in that case, if there's some new products available, right, what do we do with that? And that same, a second here. Okay, and that's also applies to the item-based. Item-based algorithms based on items. So if you look at the pretty much a similar example here, right? And then instead of based on user, we base on the items, right? Based on items. We look at this case that we look at apple, right? Then both A and B, right, likes apple. And then when we look at pears, right, then we look at A, B, and C, all like pears. So in this case, right, based on the items, then it makes recommendation of apple, right? So apple recommended to C. Okay, so this is also based on the user and item, right, relationship. And then same problem we have here. What if we have something that nobody have any experience on that, right? No ranking on that, right? No rating on that. So in that case, right, so what do we do with this? And there's also other approaches which are model-based. That's also based on the user-item, right, relationship. The user-based and the item-based are memory-based algorithms for traditional recommendation systems. And for model-based, it's based on the data, right? Try to use certain models like decision trees, right? Rule-based models or Bayes methods. to generate this model, right, to make the recommendation. So knowledge graph, right, and the knowledge graph related recommendation systems will take more of these entities, all of these more relationship, right, into consideration, relations into consideration. So if we think about one example here, right, in this triplet, we have this head entity, right? We have the relation, and we have the tail entity, so HRT, right? If we think about the Yelp dataset, that is one we use for our analysis evaluation, right? So then we look at the entities available, right? Then we have, we didn't list all of them, right? There's about 34, or at least a couple of these. But when we look at these entities, right, we have lots of information. But then if we just use a traditional recommendation system, right, not all this information are taken into consideration, right? So we look at here, we see that we have business, right? That could be business name, business information, the city, right? And the business could be maybe restaurant, right? Or spa, or like just any kind of business. So city, state, right? Style, okay, whether it's available for drive-through, right? Maybe there's some age allowed, and all this information, right? And then the relation basically is attribute, right? So if we're going to build this triplet, right? Triplet for this knowledge graph, right? We have the head entity, we have the relation, we have the tail entity. For example, if we say that we want to build this triplet for business, okay, in city and the city. So then we'll see, okay, maybe one restaurant is Olive Garden, right? And then the relation is basically in city, right? And then the city is actually Houston, right? Houston. Then another one, maybe Panda Express, right? The takeout and fast food. So then we have the in city, that's for example, maybe Los Angeles. So based on the source data, right, original data we have, what we're trying to do is to build this knowledge graph. And this knowledge graph will consist of all these relations, okay, build these relations. And then in addition to that, right, we can build all these different kinds of relations. This is another example that we build a relation between the city and the state, right, city and state. So if we're ever going to find out this Olive Garden, and we find out the city is Houston, right? Then we could this is another triplet for Houston, in-state, and Texas. So basically, knowledge graph consists of all this knowledge, right, based on the source data. And based on that, we're going to be able to find out more latent connections. So basically, by using knowledge graph, right, we'll be able to discover more latent connections among items. And then we'll explore more about user interests, right, to increase the diversity of the recommendation system for different types of relations. And also, it will provide more examinatory of the recommendation system due to the connection of the user historically liked and then recommended items in the knowledge graph. So the activation function, right, is very important in neural networks. It's basically transform the input data, right, into a certain type of output. So here we list the three pretty popular nonlinear functions, ReLU, Leaky ReLU, and the LU. So then these are the basically the figures for these three different activation function, linear and nonlinear functions. And later we talk about how we're going to study their effectiveness on the recommendation system. So our contribution, right? So we give the brief introduction about the basic recommendation system, and then the traditional recommendation system and knowledge-based recommendation system. So we propose an efficient tool. It's called the Knowledge Graph Processor, KGP, which is a user-friendly interface that can help the user to generate the knowledge graph. So if we have a raw data set, then we feed this into the KGP. Also the relationship we try to find out, right? It will generate the knowledge graph data, okay, for my data set. And we also use our Yelp Knowledge data set to test on this. And we also conducted analysis on different aggregators with the different nonlinear functions on the knowledge graph convolutional network. Try to see the effectiveness of these different algorithms. And then we release our KGP. So if any of the you're interested in try it out, like to see how this can generate help to generate a the knowledge graph, please visit our GitHub website there, and we have our knowledge graph process available there. So why we need this, right? Why we need this? If we look at any data analytics, right, we conduct all kinds of study, but then most of the time, right, probably 70%, 80% is spending time trying to pre-process the data, right? It doesn't matter we're doing this for kind of for machine learning approaches, deep learning approaches, or recommendation system. They involve lots of data pre-processing, right? So, and it's about 70 to 80%, right? So in this case, and then to understand the knowledge graph, right, and also produce this knowledge graph so that we can feed into different kind of knowledge graph based recommendation systems, right? Also takes time, right? It takes time to kind of learning it, and also takes time to process the data, right? So that's the goal here, that we're trying to provide this knowledge graph processor, right, to help the user, right, to generate the knowledge graph and then feed into this recommendation system. So if we look at right side of this slide here, this is our figure for knowledge graph processor system, right? So basically, we can process multiple data file, okay, JSON or the CSV, and also we can process certain kind of limited text file, right? So first, we can process this file and then convert it into CSV format, and then the KGP going to perform data cleaning. So we clean the data to handle the duplicated or the no values in the data set. And then after that, right, we're based on user input. The user going to let us know basically what are the entities, right? The user choose to build the knowledge graph, and then what kind of relations, right? What kind of relations? So we take those specified information, and then we generate basically extract this information from the source data, right? From the source data, and then we also based on that to build all these new data file and then assign index to that. So one thing I want to point out is here that just to make the data is more friendly for the recommendation system here, we also transform all these explicit feedbacks, like for example, if the rating is between 1 and 5, right? 1, 2, 3, 4, 5. The user probably give the rating like a 4 or 5, right, or 3. In that case, we're going to transform basically 1 to 3 to 0, and 4, 5 to 1. So then basically that becomes just yes or no, and 0 in the 1 case to fit in. It could be more complicated, but then it will increase the complexity or the time spent on that. So then after that, right, then we generate the KG knowledge graph for the recommendation system. So the Yelp knowledge graph that we use here consists of 6 million reviews, nearly about 20,000 business, like restaurants or bars, like barber shops or the spa, all kind of business. And then it provides all the categories of the locations and all the attributes that we mentioned earlier, right? The city or the state, and then the drive through all these other information. And those are different attributes. So we pre-process the data and then build the relationship based on our study of the data. Try to select what kind of relationship, right, we want to have in our knowledge graph. And then we also set up this rating data between 1 and 5 to be transformed to just 0 and 1, right? To be more friendly for the recommendation system. So this is a knowledge graph formation, right? Knowledge graph formation. We have this data set for the user, right? And that's a user. And then we also have all the items, right? All the items. And this is basically whether user voice is 0 or 1 based on the data source that we have, right? And then we build a knowledge graph with the HRT with all these triplets here. And then we have the ER, right? Basically, this is the E is basically entities and the R is the relations. So could be different types of relations, right? Like the in-city and then in-state example we talk about, or the movie example that could be the actor or the director or the producer. So here's an example that similar to the one we showed earlier. Like if we have the movie, right? This is the Star Wars, right? And then the relation is the director, right? And then the third field here, the tail here, is basically the director name, right? So then basically, based on the source data, all this knowledge is built, right? And then generated accordingly. So the knowledge graph convolutional networks, right? And we'll take all of these, right? Knowledge graph into consideration. And this is based on Wang's work from Microsoft. They have built this knowledge graph convolutional network. Now, what we use here, look at the right side of this. The raw data set will be fed into our KGP that generate the knowledge graph. And then once we have this knowledge graph, right, with all these connections with all the information, right, all the information from different entities, it will be fed into this KGCN layer. So the KGCN basically is a knowledge graph convolutional network. It will process all this knowledge, right? And then aggregate all these results and then produce prediction. So there are different type of aggregators used in the knowledge graph convolutional networks. There are sum-based, concatenation-based, and neighbor-based. So they will use the sum, right, based on the sum of this vector itself, and then the related vectors, and or concatenate, or based on the neighbors. And this is only based on neighbors, not itself. And then nonlinear functions can be applied on top of that. That we mentioned the ReLU, Leaky ReLU, and the LU. So for analyze our data, we actually conduct several different types of experiments. And then we check the 10 core, 20 core, and the 30 core. And in that case, basically we try to find out the high frequent relations and data and entities. So this basically count if they appear equal to more than 30 times. This is 20 times and 10 times. And then in addition to the Yelp data, we also use the original, movie length 200 million that was also studied in the knowledge graph convolutional network study. And then the parameter A for the leaky value is 0.2 and LU is 1. So this is based on our study. We found out, we try to vary the value of A and try to find out the best of it. Now, if we look at the Yelp knowledge graph, by using the KGP, we generate all these data set. We have the number of users, number of items, number of interactions, and then the number of entities and the relations, and then the number of KG triplets. So this is 10 core, this is 20, right? This is 30. So as we, and this is for the movie length. So as we increase basically the threshold, where we set up the 10 times or 20 times or 30 times, we can see that the number of the users, items, or interactions, entities increase dramatically, right? So from here, 1020 is about 44,000, but then it's 16,000 here. And then in terms of the interactions, right, jump from 876 to 320,000, and then to 24,000. And then for the entity, the number of entities we have from 70,000 to 25,000 to about 1,000, almost 2,000, right? And then number of relations we use here is about, keep the same, 34, about 34. And then this is the number of triplets we have in our KG. So this is about 1 million, right? This is about 627,000, and this is about 60,000, right? So this is basically the data, right? The KG information after we try to vary the threshold to for our data set. So we test our data set with basically 3 baselines. We have the KG-free baseline, basically the traditional recommendation system, no knowledge graph considered. And then we also consider second one is the KG-aware method that actually taken the KG, the knowledge graph, into consideration. And then the third one is the knowledge graph convolutional neural network, right? KGCN with ReLU function, right? And then the various different types of ReLU function, the nonlinear function. And then we use the LeapFM, it's a software implementation for vectorization machine. And then we also use RippleNet, that's basically the KG aware. Okay, so this is one. It's a KG-free, just based on the traditional recommendation, and this is based on the knowledge graph. Okay. So then our study is based on the accuracy, and then we select about 80% of the source data, right, for the testing, I mean for training, and then 20% for the evaluation, the testing. And we use the AUC, the accuracy, and the F1 score basically to evaluate our results. And then here are some of the parameters we have for our setup. When we look at the experiment results here, right, this is the one with the KG-free. There's no knowledge graph into consideration. It's only considered the user and then the item, right? And then the RippleNet consider the KG, but it's not KGCN, right? It's not considered a convolutional neural network. And then for KGCN, right, we considered different types of aggregator, the sum, the concatenate, and then the neighbor for each of these nonlinear function, the ReLU. So this is the KGCN with ReLU, leaky ReLU. And then this one is for the LU. Okay, this is with the KGCN with ReLU. And this is basically the original KGCN with the ReLU here. And then if we look at the results here, then we'll see that compared to the 10 core, right, the results we have improved slightly here. And then when we move to 20, right, and then 30 cores here, we can see we have even better improvement here compared to this original KGCN with ReLU system. So then this is for the movie length. Movie length overall, I think the results are pretty good, right? And that actually shows that because this movie length data set has more kind of study on the how to build the knowledge graph itself. So we can see how important for building this knowledge graph, because basically any data we feed into our system, right? And then if the data is well processed, then it will be more friendly to our system, right, to analyze. And then if we compare KGCN, Leaky, ReLU-Sum with the RippleNet, only consider knowledge graph, only consider knowledge graph, but then not KGCN. We can see it also performs most of the cases, right? It performs better. And then compare to this without knowledge graph, right? There's a significant improvement here, right? Based on AUC and F1. So this is basically some of the summary for the table we showed in the last slides there. And overall, we can see that KGCN-Sum and the KGCN concatenate performs significantly better than KGCN neighbor, because if you remember that we talk about the KGCN neighbor, the aggregator only considers the neighborhoods, right, all the neighbors representation. And then when we compare the different types of nonlinear functions for these aggregators, we see that the leaky ReLU performs the best out of all three. It's better than the, because it will take, when we have this nonlinear function for the cases that we have x less than 0, we don't just set it as 0. We have another case for that, right? That will take more of this into consideration. And then the LU performs worse among all three of these. So when we base out the KGCN-Leaky ReLU-Sum, we consider this case and we try to vary the different neighbor sampling size, right? These are the K neighbors, 1, 2, 3, 4, 5, 6. And we vary this. And then we have, in case of K equal to 6, we have the best of the prediction result, recommendation result here about 0.93 for 10 core, 0.903 for 20, and then 0.78 for 30 core. And then if we consider the depths, different depths of receptive, basically that's basically how far do we want to go for this knowledge graph connection, right? We can go maybe one level, we can go next level, right? We can go with the restaurant to the location, or the location to different type of, maybe different kind of type of cuisine and so on. So how far do we go, right? How deep it is. So here we have considered the depths of 1, 2, 3, and 4. And in the case of the 2 levels, where we have the best results about the 0.904 for 10 core, 0.89 for 20 core, and then 0.77 for 30 core. And then this one shows we vary the different dimension of the embedding. And then in this case, 128 give us the best results. It's close, but then slightly better than other cases. So to conclude, in our study, we basically focus on knowledge graph-based recommendation system, and we propose an efficient, effective data preprocessing and knowledge graph generation tool, KGP. And then we also use our KGP to test out the Yelp data set. And the KGP can process different kind of data file. And then we test the Yelp data, right, on the KGCN with different nonlinear functions to study effectiveness of these different nonlinear functions affecting the recommendation results. And we found out the leaky ReLU performs the best. And for future work, right, we could do a lot for the KGCN, try to add more features to give user more flexibility to generate their KG, right, to generate the one they want, and then set up limitations or give more flexibility to set up those criteria. And then we could actually study more influence of the nonlinear function in the in more layers. Right now, we only work on the first layer of the aggregators. It could be work on more nonlinear function, more layers in the KGCN. So here are some of the references, and thank you so much. And if there are any questions, you're welcome to discuss now. Thank you.